Hi guys, so this video is just a video to demonstrate a third year university project that I had to do for Deakin University, and the problem was to create a system to track a pendulum. So it involves a bit of machine vision and some motor control systems using feedback from the machine vision, and we're asked to do it using a Raspberry Pi platform or similar, testing and deploying a model to control the system in MATLAB Simulink Simscape environment. So yeah, I hope you enjoy the video. Okay, so here's my pendulum tracking system. If I turn the laptop around, you'll be able to see my camera there. There's the webcam on an X and Y gimbal. Just two servos, but they've had their control systems gutted out. They instead have a H bridge here that's connected to both the DC motors in here. I'm just using the DC motor and the gearbox. And here is the Raspberry Pi that controls it. It's on an Ethernet link to the laptop that you're looking at me from. And it is tracking the pendulum. Obviously you can see the output of the camera here, and there's a pink cross in the center of the frame. That's the target location for the camera to center the ball onto. The color thresholds are currently trained to the ball, these color thresholds over here, which go through the machine vision system. And the ball has a red cross that gets drawn over it when it's detected, and the centroid of that cross is the control system's aiming to center the camera on there with a little bit of tolerance for error, which is basically just letting the energy loss in the motor happen through the PWM when the signal's not strong enough. So there's our pendulum back there, and let's see if we can get it to work just a little bit. So that's it following the pendulum. It's a little bit hard to get it to follow any closer than that. We get a lot of overshoot, and I think it's beyond the performance of the Raspberry Pi and possibly the motors in the current setup I've got, especially with the amount of time I've got to optimize. I've done a fair bit of optimizing on the code, like using the highest optimization on the GCC. I'll go through that later. But yep, that's oh, there we go. There's a bit of an error. Sometimes we get that. But if I turn the motors off for a second, we can recenter back on the thing. Turn it back on. There we go. And just to show you that it has two axes tracking. There we go. Whoop, error. Okay, so yeah, we can play around with the P, I and D values here and try and get it to work better. I've been playing around with it, but it just seems like I think perhaps the actual output of the motors is an issue, and the PWM signal on the Raspberry Pi. So I've just moved my webcam across. So here's the system here. See if I can zoom in on that for you. And so basically what it is the machine vision system. Let's see if we can look at this while it's live. This is the machine vision system here, with the Raspberry Pi camera coming in the RGB color channels. Each one of those thresholds that we had on the screen back here on the control dashboard. Back. What's happening here? So these color thresholds that we can train, they come out in the machine vision here. They control these. If it's greater than the bottom threshold, like the red color channel is for each pixel if it's above the bottom threshold and below the top, and so there we go, below and above and below, bottom and top, and that gets to be a 1. And same for the other 2 channels, and they come across and feed into an AND. So if all 3 of those conditions are met, then that pixel becomes a 1, which is white, and it goes into a black and white image fed into the blob analysis tool. In the blob analysis, it spits out, we've got the centroid and bounding box getting spat out. You can see them on the output to the box here, and we're filtering that so that the minimum size has to be 35 pixels and the maximum is 1200 pixels. That helps filter it even more after our color channels have filtered. Then we just do a data type conversion so it's compatible with the draw X, these different tracking things. This is currently commented out at the moment, but basically we can get a black and white thresholded image so that we can tune out the noise even further. It makes it a lot easier to see noise in the image. I might just run that now while I'm talking along, comment them. So we'll go, I think it's Control Shift X, isn't it? No. Yes it is, but it didn't work. Uncomment all these and I'll start the model up, see if we can get it to run and run you through it so that you can see the effort I've gone to for filtering. So running that, and while we're waiting for that to load, we'll see how the other half of the machine vision works. Oh, we can't go through it, so I'll just pause for a second. Okay, we're back. So that's loaded now, just get rid of that. Something else I'll show you is that I've set up the compiler for execution efficiency just to try and make it run fast. It didn't seem to make much of a difference, but I've got another video I'll tack on the end of this just to show you guys that. Here is the rest of it. So we've got the black and white stuff uncommented, so we'll just have a look, click on that, see if we can compare. So there's our frame. It's got a white box 1 pixel wide drawn around it and then a black X drawn in the middle. Probably don't need that, but basically you can see that the only white pixels returned are within those color thresholds. We can probably optimize a little bit because there's a little bit of black in there, and that's one weakness of the system. As the lighting changes, I've got a couple of windows here, it's cloudy. If it's sunny, we have to retune the system. And also, I think the white balance of the webcam is constantly updating, so it sort of scales all the colors according to the light conditions. But yeah, that's a really handy tool, because if I go to our color channels, I'll just bring that black and white box back up and put it over here. If we change our thresholds a bit more, you'll see noise starting to come in, but if we filter that noise out by doing this, it goes away. But even with a little bit of noise in there, because we've got the minimum blob size and I've only got maximum of 1 blob returning, it's only going to still return the ball here. But if we go way out of range, there you go, we see that the noise, the camera's just gone mental because it's picking everything up as a blob. But bring those color channels back in and put the camera back in the area of interest, and we should be right. So I'll just bring him back down. Anyway, I can't remember where I had it, but there we go. It's picking up the ball. There's a fair bit of noise still, too much red in the low end. Yep, there we go. So okay, so that's some of the machine vision. The other thing we have is the centroid comes up to here, and the bounding box also comes out. I actually commented out the bounding box draw onto the, this is to feed this camera system here basically, just so we can see what's happening. This is actually how we're monitoring whether the system's performing as we want it. I've got the motors turned off at the moment, that's why it's not doing anything. But so this this here just draws that red X mark there based on the centroid coordinates of the detected ball from the blob analysis. These transposers here just to turn the image 90 degrees. For some reason it's rotated 90 degrees and this fixes it. And then that's to draw the markers, the pink plus. So we've just got the colour value for pink there, and we've got the colour value for red there. So that's the red cross, and then the pink cross, that's the centre pretty much of the image because we've got 120 by 160. And then that comes out to the video viewer, which is video viewer 2 here. Okay, so that's our machine vision system. And importantly, these are the centroid coordinates of the blob. And looks like we've got a little bit of an error here where it's sometimes not detecting the ball. That's because it's getting sunny in here again. When it goes to -1, that means it's not detecting it. But when it does come up, we can see that 74 and 80 are close to the center of the pixel, which is about right. It's in a fairly central location of the image. And so they get pulled out here using these, I can't remember what they're called, selector. So it just selects the first index. Well, we're 0 based at the moment, so it takes the first index and the second index from that centroid data and spits it into these, what are they, outports, X coord and Y coord, and then they get fed into our PID control system. So there's our X there and our Y there. So if we follow that through, that X coord goes to a go-to, which gets fed here. Basically we're saying if X coord is greater than 0, because back before when I said we had those -1s, that means that the blob's not detected. We don't want to have any output. We don't want to run an error analysis or whatever on that. So if it is detected, then we spit in X coordinate and subtract that from 80, which is the central pixel that we want, is our target value, where we want the centroid of the blob detected to be, and we subtract that from 80, which then gives us an error value, and the magnitude of that obviously gives us which side of the image is on. So that then will give us the direction that the motor needs to turn on to control about the Y axis. So when it turns around the Y axis, it's going that way, affecting the X coordinates. So if the error value is greater than 0, we turn this pin on and this one off, and vice versa. And they're the two direction pins on the H bridge. So they're at pin 27 and 17 on the Raspberry Pi. And we've got a bit of, this is the PID spits out its value. I've got it clipped to 50 and -50 at the moment. And then so I scale that, because the PWM works from 0 to 1, I scale it 0 to 1 by dividing the output by 50. And I've also got a pre-scale here just to play around with the PWM, because the motor and H-bridge combination doesn't seem to respond to low duty cycles. So that was just to scale the PWM a little bit. Yep. So then we take the absolute value, and that goes so that it's between 0 and 1, not below 0. And then that goes into the PWM pin 21 on the Pi. So that's for one motor that's on the Y axis. That controls the speed of the motor. And for some reason only below 100 Hertz would work, even though it's a L298N H bridge from ST Microchip, or whatever they're called. Their data sheets, I think, say 2 kilohertz is meant to be best, but for some reason 50 hertz was working best. 2 kilohertz, the motors were just making a high pitched noise. Yep. So that's that. Same for the Y. So did I forget something? Yeah, we're subtracting from 80 because that's the difference from the center pixel. So the x-axis controlling the rotating about the x-axis, which we influence the y coordinates of the image. So we've got the y coordinate coming into this one. Only main differences are the center pixel is 60 because of the dimensions that we've selected for the image analysis. And the only other difference really is the pins, the output pins. So obviously they've got to be different, but they're going to the same H bridge because it's a dual channel H bridge motor controller. And yes, that's pretty much the Simulink model, I guess you call it, or whatever, of the control system. And that's abstracted here to this. All those values here for the PID are controllable, as well as the PWM prescale. So we've got a control dashboard here, and there's our abstracted system. A good thing to note, I didn't write one line of code for this, which was, I thought, a bit of an achievement. I've done this thing similarly before in MicroPython on a microcontroller optimized machine vision thing called OpenMV, but they required writing code. This one didn't. It's all that graphical Simulink block stuff. It's interesting to learn. I could probably get it to work better if I had more time. Other things to discuss, I guess, are the filtering. So that, you saw some of the filtering I did with the blob analysis and the color channels. I was going to look at doing like a finite infinite response filter, where basically like a weighted moving average, or whatever you call it, moving average filter to average the blob centroid out. This noise wasn't actually that common, this movement. It's just like I said, because it's getting a bit sunny now, but some of the other videos that I'll probably put on this show it quite steady. And because the system's a bit slow to respond as it is, I didn't want to add any more lag time by averaging out the last, say, 10 values of the centroid. I think it would have just made it perform even more poorly. So I left that out. So that would have been the main filtering, I think, that we would have used. All the other stuff that was taught in the unit, I thought, was mainly for more of an analog application, and I didn't really want to go into pulling the webcam apart and start filtering that. They've probably already got some of that circuitry in there with their, sensor setup. And same with the Pi, it would have its own filtering, and same with my power supply. That's something I forgot to mention as well. It's just my lab supply at home. That's what's powering the system, apart from the Raspberry Pi, which has its own, I'm just using the USB. You can just see it, but that's the official Raspberry Pi 2.5 amp power supply going to the wall, to micro USB into the Pi. Oop, lost my monitor. There we go. And that's about that. I'll pause you for a second. Okay, I thought I'd just go through the fine-tuning of the color thresholding a little bit more, so that we've got a bit of noise here now, and we've actually picking up a blob, which is my arm, which is kind of a similar color to the ball. Or the pendulum, I should say, pendulum bob. But there's a little trick here that we can use, which this is the video viewer down here. Now, if we click on this little pixel information viewer, it opens up this window, and if we zoom in enough, we get each of the color channel values. So if we overlay that viewer on the ball there, see if I move that around, there's our X in the middle. We don't want that, we just want these bits. You can see on the black and white that those pixels aren't meeting our threshold conditions for some reason. So if we analyze these pixels, we kind of see that all the red's up pretty high. It's all above 240. So I might just jack that threshold up a bit. We've just lost a lot of noise in the background, which is good. and green is around 140, 150. So let's have a look down here. Probably narrow down our green band a bit more. That'll just filter out any noise that might come up. And same for blue. Blue is around 100, 80, 100. Let's try. So we've got about 120 there at the moment. So just narrow that down. Yeah. Okay, 150. Looks good. So yeah, we've got a fairly solid blob in the middle and zero noise again. Yes, and there's a little bit of pixel movement, 1 pixel this way, that way. I think that's negligible noise, really. The PWM won't even really get a response from the motors at that movement. So, yeah. There you go. That's tuning the color system. Okay, here we are back again. So here is the pendulum system modeling. It's going a bit slow because I think I've got so many points getting calculated, but we'll just stop it there. So that is our pendulum system in Simscape. It's basically a just a long, I think it's a cylinder on a revolute joint. We've got gravity going downwards on the y-axis, and we've put some friction, I believe, here. So damping coefficient, that's to represent the energy loss in the system. If you want to know more about the mathematical stuff, I've put a little bit in the report. Didn't have to do too much maths because this is Simscape multi-body. They were doing it all behind the scenes. But yes, I do understand it. And that was the main information that I had to put in there. We've got position sensing for the modeling. So the purpose of this model was to basically so I could understand if I could use how I could tune a PID to the kind of frequencies that we'd expect with the pendulum, and also whether I can use PWM to control a H-bridge and DC motor to get the response that we want. So yeah, that's the Simscape multi-body pendulum model, and that's the sensed revolute joint angle. Comes into a Simulink signal, feeds into our, that's a scope there, feeds into our error calculator. The other part is we've got our Simscape, I guess this is Simscape multi-body as well. We've got our DC motor and H-bridge with a PWM feeding into the H-bridge. And there's a ideal rotational motion sensor that feeds into another PS2S converter, Simulink signal converter. So the difference is found between the motor angle and the pendulum angle, and that is converted, that is put into our PID, and then our PID, we basically, I did a auto tune and we got these values, which came out pretty good after I'd put in some more realistic DC motor things that I got off a data sheet online. So I just got some of these values, mechanical and electrical, off a data sheet just to get working. Excuse me. And fed them in. Once that happened, then if I bring this scope up, here we can see so we've got the PID controller output. That's a really fuzzy line. It's doing a little bit of a signal, and the motor's responding accordingly. So the pendulum angle that's the sensed pendulum angle, the red, and the blue is the motor's angle. So it's responding quite well. There's a little bit of ripple, especially on the peaks and troughs of the sinusoidal wave. But basically after a little bit of playing around and auto tuning, that's what I got. I had a little bit of trouble at the start, basically because my error calculation was incorrect, and like I said, I didn't have very realistic things in the DC motor. What else can I explain about this? So this models the direction control by having a reverse pin. So that's similar to those 2 pins on the H bridge that I explained earlier in the real setup. So instead of having 2 pins that are 0 and 1 or 1 and 0 for forward or reverse direction, this is just a 1 or a 0 that's based on the sign or the polarity of our output of the PID. So that tells us to go forwards or backwards, the motor. And the PWM is, we just get the absolute value out of the PID, feed that into the PWM generator, and then that gives us our magnitude. So there's our magnitude and direction of our angular velocity for the motor to track the revolute joint. Yep. And that's how I came up with PID values to use in the real thing. Then they got fine-tuned from there based on the output of the video screen you saw earlier. So if I had more time, I would have probably liked to have done a more realistic model. I did start doing some trig calculations here. So if we open this up, this was basically the X, we've got the X and Y coordinate, which is more like towards what I did in the real setup. So I just used trig, the length of the pendulum and the sine and cosine to get the X and Y coordinates. And I was going to use them to do 2 PIDs and yeah, do some reverse trig on the motor angles to get that going, but didn't have time. But what this did do was allow me to make sure that the PWM signal was coming out correct. How do I zoom in? So if we ignore the green, we should be able to see that the PWM is, it's a bit hard to see here, but the PWM is scaled to the X coordinate, I believe. Basically I use this just to understand what's going on a little bit and make sure that things are right. Yeah, so that was a handy thing to do, but more time I would have done a more realistic model, maybe even measured the parameters on the DC motors I'm using. But there was a lot of errors that came up with this as well. You guys are aware of the original error that MATLAB support helped us with, but even beyond that, since then, I've got a few errors I might be able to just pick up here. I've got screenshots of. These will go in my report too. Just before I do that, this is what some of the PID outputs I had before I figured out the errors. You can see they don't track quite as well as the model we just ran. But yes, we've had this one. Some of the people that were in my team have had this as well. There's the checksum error. And so what we've got to do then is, if you've got the checksum error, you've got to shut everything down and log into your command prompt, SSH into your Pi, enter your password, remove all the files that are related to your model, exit out of that, rerun your model another couple of minutes, then run and hope there's no more errors. So that's it, one of the errors. Another one, lost packet. Lost packet. So you're running your model and then it just stops running. You've lost your packet. You can't close your Pi down, you can't SSH in or anything. I think it's actually the Pi crashing. Have to power it, full power cycle, start the model up again, another couple of minutes compiling and loading. So that's that one. And MATLAB itself crashing. a couple of times a day. This one, the other one's probably about 10 times a day each. It really adds up in the time. That's one of the reasons why I couldn't get the system working as well as I like, but I did get it working to a point, and I think this needs to be considered as reasons, things that we've sort of overcome to get past that. Okay, yeah, and if I had even more time, I would have loved to go into a Kalman filter, but I didn't have that time. What else did I want to show you? You've seen that kind of stuff. Yes, here, this is probably a good one to look at. So when I first connected up the hardware, I wanted to make sure I was getting the right outputs on the hardware. And so I used my Celier logic analyzer. Have I got that here at the moment to show you? Where'd you go, Mr. Celier? Here it is. This is probably one of my favourite things to own. Half price, student discounts, about 250 Australian. It acts a little bit like a low speed scope, but actually is also an awesome logic analyzer. They weren't using any protocols today, but you can use all different kinds of protocols on it. And you've got timing analysis, and you can have digital or analog view. So basically I just wanted to make sure that my hardware, the pins on the Pi, were doing the right thing. I was moving the pendulum to the right and the left of the center of the screen, and lo and behold, our direction pins were inverting, meaning it knew to change direction of the motor depending on the sign of the error, go this way or go that way. And this is a PWM signal. So it was working, and that just helped me verify, do a bit of troubleshooting when things weren't working very well. There's a better view of some of the PWM. Yeah, so just to talk through some of the things I've done. I'll pause you guys for a second again in case I think of anything else. Okay, thank you for watching. That pretty much summarises the project. Probably a bit of a long video, I apologise for that. But there's two appendices to the video as well that I'll put on. One is just about the steps I went through to optimise code execution on the Raspberry Pi to try and get better system performance. It didn't really make much of a difference in my opinion, but it was worth a try. And also just a bit of a run through of the hardware so that you can see it. Basically the servo motors, which are not servo motors anymore. Disconnected the control system stuff here, soldered these two on, which come out to these motor terminals. This is not used, but I just left it on there because I probably want to reuse my servo later. And then put this lid back on here. Okay, code generation. Optimization. Maximize execution speed. There we go. Wondering about these two here. Levels to maximum. We don't want readability of code or anything. Okay. Where's the GCC? Here it is. We're in C. We need GCC. Something I can show you is that here it is. So options that control optimization for the this is the GCC, the GNU compiler collection, or whatever we call it. So you've got different options. O, putting the flag O in the compiler command thing, you can have different levels. Level 1, and I think at the moment it's on level 2, O2, but we can go to O3 or O, we don't want size. and we don't want to reduce compilation time, we want fast. Disregard strict standards, and compliance enables all of that, so this is what we want. So let's try that and see what happens. Toolchain details. Now, there was a way I could get into these. Specify, there we go. But look, we're on 00 at the moment. Faster runs is 02. Faster builds is 00. Okay. Specify, let's try. O fast. Now that's the right spelling, isn't it? Yep, no capitals. O fast. Okay. Apply. Now this thing here, we want to set objectives. Execution efficiency. We don't care about any of that other stuff really. Okay. Now let's check the model. And this is what we want to check, the whole combined optimized thing, and that falls yes. Okay. Loading checks. Okay, when we've done that, so we get 5 pass, but 4 with a warning. We've got a few. So all these things need to be changed. Tunable parameters, we put them into inline in the code, I guess, and all these other different things. I was a little bit worried maybe about root level IO, zero initialization, and those two, but we'll try, see what happens. See if it runs better. Okay. All parameters have been set according to the recommendation. And done. Support for continuous non-finite numbers. We're not doing production code. We're not doing production code, so don't care. One-based indexing. Now we need 2, 0, and 1. Yes, okay. So we need to change our indexing here. It makes it more efficient. Cancel and just see what that started out as. 1 dimension. We'll go 0 based. This will be 1, 1. Okay. And then it'll be 0, 0. Okay. Respect your local environment. Come on then.